What are you, 12? In this video, I'm going to do the first part of the complex numbers question from the test you did on Thursday, and it's one where we're given a quadratic to solve, but the quadratic has got imaginary coefficients. So we can do this in two different ways, and if you're in my class this year, I'd like you to make sure that you are confident with both of these methods. The one that I think is slightly better here is using the quadratic formula, but I also want you to see how we can do it by matching the real and imaginary parts, because that's a really good technique to know for other situations too. So just because we've got iz squared plus 2z minus 3i equals 0 doesn't mean that we've got problems with the quadratic formula. If you think about when we proved way back when how the quadratic formula works, all we did with this is that we basically completed the square, and from there we got x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. And there's nothing in there stopping us using that when the a, the b, and the c are complex numbers instead of real numbers. So that's what I'm going to do here. So we'll start by saying a is equal to I, b is equal to 2, and c is equal to negative 3i. Now I'm going to substitute in to solve for z. So z is equal to negative 2 plus or minus the square root of 4 minus 4 times I times negative 3i divided by 2i. I'm cleaning that up quite slowly because I don't want to muck up this step. So I've got negative 2 plus or minus 4 plus, now 12i squared gives me negative 12. Divided by 2i. So we're just about there, right? So negative 2 plus or minus the square root of negative 8 over 2i, which is equal to negative 2 over 2i, plus or minus 2 root 2i over 2i. So what happens here is we get negative 1 over I plus or minus root 2. We can fix up the negative 1 over I by multiplying by I over I. Now, usually, of course, we multiply by the conjugate, right? And the conjugate of I is simply negative I. We don't need to have the negatives in there, right? So that will work out just fine. So plus or minus root 2, and here I squared gives me negative 1, so I'm left with I plus or minus root 2. So you can see that my two solutions are root 2 plus I, and z2, the second one is negative root 2 plus I. Now just make sure you understand why those two solutions are not conjugates of each other. It's because the conjugate root theorem doesn't apply, because our coefficients in here were not real numbers. So that's 5 marks done that way. Oh, I don't know where there's my picture there. So we've done it that way. Now I'm going to do it the other way, equating the real and imaginary parts. So for this method, we'll start by saying let z equal x plus iy, and then we're going to substitute that in. So we'll have I times x plus iy squared plus 2 times x plus iy minus 3i is equal to 0 plus 0i. So I think this is the key step here, is that 0, when we're working with complex numbers, means 0 real part and 0 imaginary part. All I have to do now is to expand this and this, clean it all up, and collect up the real bit and collect up the imaginary bit. So we get I times x squared minus y squared plus 2xyi plus 2x plus 2yi minus 3i is equal to 0 plus 0i. So for the real part here, I'll go a little bit slowly here. So we've got x squared minus y squared I, and then this becomes a real part. So this is going to be minus 2xy plus 2x plus 2y minus 3i. So the real part is quite short. We've got 2x minus 2xy is equal to 0. And we have to have both of these things being true. And then we have to have the imaginary part being true. So x squared, what have I got? X squared minus y squared plus 2y. minus 3 equals 0. So please don't stop watching if you think you've got it this far, because most of you have gone wrong at about this point. So what I have to do now is find a combination of x and y that make both of these things true. And I know that x and y have got to be real numbers, right? Because my z has to equal x plus iy. And these are real numbers in there. Okay, so the first thing I'm going to do is I'm going to try and solve for one variable. And I'm going to pick on this equation because it's cleaner. So how can I do something here? Well, I've got a common factor of 2x. So 2x times 1 minus y is equal to 0. That can be true if x is 0 or y is equal to 1. So we're going to take x as 0 and we're going to chuck it in here and see what we get. So if x equals 0, we're left with negative y squared plus 2y minus 3 is equal to 0, which is a quadratic. Y squared minus 2y plus 3 equals 0. Now you can solve that however you like, but what you'll find is that y isn't real, but we need to actually just go through and do that. So I'll do completing the square. So y minus 1 squared minus 1 plus 3 equals 0. Y minus 1 squared is equal to negative 2. So y is equal to 1 plus or minus the square root of negative 2. Now that's enough to say is not a real number. So it's not valid. So that means we can ditch this one. So x equals 0 is not a solution because it's not going to give us a y value that works. So now let's work out what happens if y is equal to 1. So if y is equal to 1, we get x squared minus 1 plus 2 minus 3 is equal to 0. That cleans up to give me x squared minus 2 equals 0, giving me x squared equals 2. And you should be liking this by now because you know where we're going. X is equal to root 2 or negative root 2. So z is equal to root 2 plus I, or z is equal to negative root 2 plus I. Okay, so obviously we get to exactly the same answer. So I don't know about you, but I feel like there are a lot more places to go wrong with that, but there's also quite a lot of nice thinking involved that I want you to understand. So this is a question that I think is worth coming back to between now and the Cambridge exam. All right, so just put a little note in your revision book saying that this complex numbers question is a cool one that you should have another look at. I'm going to do the locus part in a separate video because this is 8 minutes long already, but this is coming up in a few minutes time, as long as the dog stays sleeping. Thanks for watching.